video, we're going to cover some chapter 13 practice problems, so let's get right into it. So the first question, which molecule would you expect to be more soluble in ethanol, CCl4 or CH2Cl2? Explain your choice. So ethanol is the solvent, and it is a partially nonpolar, but also partially polar because of that OH group. So CCl4 is a completely nonpolar tetrahedral arrangement because you'll have the central atom as the carbon, and then a tetrahedron is where you have four atoms attached to the central atom in equal and opposite directions completely. So that means these CLs will cancel out and it will be net symmetrical in all directions, meaning it's a nonpolar molecule. So it will not have a very good solubility with ethanol, which has a high polar characteristic because of that OH group. So CH2Cl2 is a better choice since it is also tetrahedral, but it's asymmetrical due to the two different bonds. It will have a CH bond, which is a nonpolar bond, but it will also have CCl bonds, which the bonds alone are polar, but they will not be symmetrical if you only have two of them. You would need to have all four, like the CCl4 molecule, in order to be completely nonpolar. So the answer would be, it would be the CH2Cl2. Next, more about solubility. Between water and hexane, pick an appropriate solvent to dissolve each of the following solutes and state what type of intermolecular forces. So before we start A through F, intermolecular forces, you're always going to have London dispersion forces. These occur, or these are weak transient interactions that occur and kind of make an induced dipole. And they always occur. But there may be intermolecular forces, for example, between polar molecules that supersede or have much more binding energy compared to the weak London dispersion forces. So they all have London dispersion, but on top of that, let's see what they have. So for A, methanol. Methanol is similar to ethanol in the previous problem. It is polar, and it's actually a little bit more polar than ethanol. So it will react and it will dissolve in water. So that's water because water is polar. Lithium nitrate, it's ionic, so it's going to form an electrolyte and a strong electrolyte because both lithium and nitrate are strongly soluble ions. So water is the answer for that one as well. Coconut oil, we don't even need to know the formula. It's an oil, so it's going to be some kind of long chain or branched hydrocarbon with just CH bonds, so nonpolar, and hexane would be the answer. Acetic acid, it is a weak acid, so it's a weak electrolyte, but it's an electrolyte. Therefore, it will go into water and it will dissolve pretty well. And you also have that carboxylic acid group, which is very polar. So yeah, it will look like this. So that's the acetic acid structure, and it will be polar and dissolve in water. Toluene is hydrocarbon, so you're only going to have hydrogens and carbon. It's going to be a nonpolar structure, so it will dissolve in hexane. Now, dimethyl ether, this is a tricky one because dimethyl ether has some polar and nonpolar characteristics. So if you draw the Lewis structure, it looks similar to water, but it has two methyl groups instead of the hydrogens. This means it's going to be a little bit polar because of this bent structure, but it also is going to be nonpolar due to the larger than hydrogen atoms over here, where you have in water it's a hydrogen, but here it's a methyl group, so it's going to be a lot larger, so it's going to have a net mostly nonpolar arrangement or nonpolar identity, meaning it's going to mainly dissolve in hexane, but only weakly dissolve in water due to that polar characteristic. Next question. The enthalpy of solution for cesium fluoride is negative 36.8 kilojoules per mole. This is the enthalpy, so delta H solution. What can you conclude about the relative magnitudes of the delta enthalpy of the solute and the hydration? So what we know is that the enthalpy of the solution is equal to the enthalpy of the solute plus the enthalpy of hydration, because once you dissolve something, a solid particle, there are two processes going on. The first of which is the solute breaking apart, which is your enthalpy of solute, and then your enthalpy of the water molecule actually breaking apart and facilitating the destruction of the salt molecule. And this is called your hydration, or in other words, that's hydrating the molecule, making the water molecules have an interaction with the solute particles. This is hydration. So you have both of these enthalpies added together to make the complete enthalpy of solution. Now, enthalpy of solution is negative, therefore it's exothermic. That's good to know. But specifically, if we look at our delta H solute, this would help us find the answer because we know it has a relation to lattice energy. It's actually the opposite of lattice energy because lattice energy is always a negative number, right? It represents the energy released on the formation of a crystal lattice. The enthalpy of solute is breaking apart that lattice, meaning the enthalpy of solute is going to be always positive. So if the enthalpy of solute is positive, and we know the enthalpy of the solution is negative, the enthalpy of hydration must be a larger negative. So the enthalpy of hydration in magnitude is more than the enthalpy of solute. Also, it's negative. That's what we can conclude. Next one, similar concepts. So silver nitrate has a heat of hydration. So this time we have enthalpy of hydration, put hydration, of negative 843. And a heat of solution, so delta H solution of negative 23. What is the lattice energy? So we can use the same equations that I wrote on the previous slide to where our solution is negative 23, our hydration is negative 843, plus the enthalpy of the solute. Now we can solve for this, and we get positive 820 kilojoules per mole for the enthalpy of the solute. But we're not being asked for that. We're looking for the lattice energy. And we know from the previous slide, the enthalpy of the solute equals the negative enthalpy of the lattice energy. So we can just take the negative of this, and we get negative 820 kilojoules per mole for the lattice energy. All right, next question. Let's get some math involved here. So how many milliliters of water, if water has a density of 0.998 grams per milliliter, are required to dissolve 25 grams of urea and thereby produce a 1.65 molality, or molal? That's what the little m means, molal, not meter or anything like that. Molal solution of urea. And here's the formula for urea, and the molar mass is given. But, on exams, the molar mass may not be given, but it's a quick calculation. So what we know about molality is 1.65 molality equals the moles of solute, spelled solute wrong, solute divided by kilograms of solvent. That's important to know. So let's first figure out, it's a good strategy in these type of word problems. Whenever you're given a grams, always convert it to moles. That'll be a great strategy. It'll always help you out in some way. So we have 25 grams divided by 60 grams per mole, which would give us how much urea? That would be 417 moles. So you have 0.417 moles of urea. Now that's the moles of solute. So we can plug that into our molality. So we have 1.65 equals the moles of solute, which we know, and we can determine the kilograms of solvent. And remember, what are we trying to achieve? How many milliliters of water or milliliters of solvent? If we have kilograms of solvent, or the amount, we can then convert that into milliliters using the density. So we can solve for x, which is 0.253 kilograms. Or this can be converted into grams of 253 grams. We can then use the density, which is grams per milliliter, and we can multiply by 1 milliliter per 0.998 grams. The grams will cancel out, and we get around the same number, 253.5 milliliters. And with proper sig figs, since both of our measured numbers in this question have 3 sig figs, 254 milliliters would be our best answer. Okay, moving on. Next, calculate the molality of a methanol and the mole fraction of solvent in a solution that is 7.5% by mass of methanol in ethanol. All right, so we're mixing methanol and ethanol. We have 7.5% mass of methanol. So whenever you have a percent mass that is given, all that means is the amount per 100 molecules or in mass. Whenever you're given a percent by mass, this means in any mass unit, for example, 7.5%, that means 7.5 grams out of 100 grams of the solution. So let's use that number, 7.50 grams of methanol. And then the rest of it, which is 100 minus 7.5, that's 92.5 grams of ethanol. So this is the solution. It's created with these mass values. So if we're first finding the molality, we need to figure out two things. Just like the previous question, we had molality. We need to figure out the moles of solute, which is the methanol, and the kilograms of solvent, which is the ethanol. We already have the kilograms of the solvent because it's the grams here, and we can just convert it to kilograms. But for the moles of the solute, we can easily convert the 7.5 grams 2 moles of methanol by dividing by the molar mass. The molar mass of methanol is 12 plus 4 for the hydrogens plus 16, which is 32. 32 grams per mole. So 7.5 divided by 32 is 0.234 moles. So to answer part A, for the molality, we take that number, 0.234, and divide it by the kilograms of solvent. So 0.0925 kilograms. And this gives us 2.53 molal. Next, for part B, the mole fraction. So we need to figure out the total number of moles and determine the mole fraction of methanol. We already have the mass fraction, but the mass fraction does not ever really equal the mole fraction. They might be close, but they're never really going to be equal. So we have the moles of methanol. We then need to figure out the moles of ethanol. So we have the mass of ethanol. We can now use the molar mass to determine the amount of moles. Now the molar mass of ethanol, the molecule is a little bit bigger. It differs by a CH2. So we can just take 32 and add a CH2, which would be 2 plus 12, which is a total of 46 grams per mole. We could then take 92.5 divided by 46 grams per mole, and we get around 2 moles, 2.01 moles. So to determine the mole fraction, we take the moles of the solute divided not by the moles of the solvent, but by the total moles. So our mole fraction would equal 0.234 divided by 2.01 plus 0.234, which equals 0.104, so around 10.4%. Nice. Moving on. Switch colors here. Let's use blue this time. So at 25 degrees Celsius, an aqueous solution that has 25% by mass of sulfuric acid has a density of 1.178 grams per milliliter. Calculate the molarity and the molality of this solution. We have 25%. Like I mentioned in the previous question, we can convert that to grams of a total solution of 100 grams. So this means we have 25% or 25 grams of H2SO4, which is the solute, and the solvent, which is unknown, we have 75 grams of it, but we do know the density of the solution. I'll just put solvent. Oh, it's aqueous, so it's water. Okay, Next, we can find the moles of the solute because we're first being asked to solve for the molarity, and then we're being asked to solve for the molality. In both cases, we need the moles of the solute. So we can divide this 98, which is the molar mass of sulfuric acid. This gives us 0.255 moles of our solute. So for A, we're being asked to find molarity. That is moles of solute divided by liters of solution. We don't know the liters of solution, but we can easily find it out based on the density. We know that our hypothetical solution using our percentages has a total mass of 100 grams. So if we had 100 grams of this solution, what would be the volume? So we can divide by the density or multiply by 1 milliliter divided by 1.178 grams. Grams will cancel, and we will get 84.88 milliliters. So for A, which is the molarity, we can take the moles of the solute, 0.253 moles, divided by the liters of the solvent, or the solution, sorry, 0.08. We can just round it to 85 liters, which gives us 2.97 molar, or around 3 molar. Okay, for B, we are calculating the molality. So we need the moles of solute. We have that. Good start. And now we need the kilograms of solvent. And that's already given because in that percent, we know that since it is 25 grams per gram, 25%, 25 grams out of 100, the remainder being 75 grams is the solvent, which can be converted into kilograms, 3.37 molal. All right, moving on. We have a 1.6 molal solution of methanol in water and has a density of 0.984 grams per milliliter. What are the mass percent and the molarity? Okay, so this 1.6 molal, we can interpret it as we have 1.6 moles of solute or moles of methanol in 1 kilogram of solvent. So the mass percent, 1 kilogram of solvent is a mass. Now we can convert this 1.6 moles of methanol into mass by multiplying by the molar mass of 32. And I got that 32 from determining the molar mass of methanol, which was previously discussed, and you can calculate it as well. It's 32. So you multiply that together, and you get 51.2 grams of methanol. For the mass percent, we can take that 51.2 grams, divide it by the total grams, not just the solvent, because mass percent is the mass of the solute divided by the mass of the solution. We know that from this 1.6 molal, 1 kilogram of the solvent is there, but the total solution is going to be 1,000 grams, which is 1 kilogram, plus that mass of the solute, which is 51.2, and this is going to equal 0.0487, and that can be converted to a percent of 4.87%. Okay, the next question is what is the molarity? So the molarity is our moles divided by our liters. Now in this hypothetical solution where we have 1.6 moles, let's use that. We already have a mole value. So 1.6 moles divided by our liters of solution. From here, we know the solution's mass was calculated using the molality, or calculated using the mass percent. So the total mass is 1,051.2 grams. Using the density, we can convert this into milliliters by dividing by the density like so. 1051.2 divided by 0.984, and that is 1,068 milliliters. In other words, 1.068 liters. So we can make this division of moles divided by liters, 1.6 divided by 1.068, and we get 1.498 molarity, so molar, and that can be rounded to about 1.50 from proper sig figs. All right, one more. Let's talk about Henry's law. So Henry's law, let's write the equation. S equals KH times P, where S is solubility, it's in molar. P is pressure in ATM, and KH is the Henry's law constant, which is in molar per ATM. Otherwise, the equation wouldn't work, since all the units must cancel out, or they must satisfy the equality, in other words. Okay, so let's read the question. What mass of O2 is dissolved in 1 liter of water under atmospheric conditions with a partial pressure, so we're given pressure, 0.22 ATM. The Henry's law constant is 1.3 times 10 to the negative third. We're given that as well. So from that, even if you're not sure what the question's asking, mass, there's no mass in this equation. We're given pressure and we're given the KH. Let's plug it in and see what we get. So we have S equals 0.22 times 1.3 times 10 to the negative third. For S, we get 2.86 times 10 to the negative 4 molar. All right, now this represents a solubility. At this condition, the solubility for oxygen is only 2.86 times 10 to the negative 4 molar. So it's saying what is the possible mass that is dissolved at this solubility threshold in these conditions? Well, we can go from moles or from molar to mass, because we understand that to have this molar, and it was dissolved in 1 liter of water, so we already know that. So 2.86 times 10 to the negative 4 molar equals the moles of oxygen divided by 1 liter. So we can calculate the number of moles of oxygen, which, because it's divided by 1, happens to be the same thing, 2.86 times 10 to the negative 4. Excuse my handwriting there. So from this, we know the molar mass of O2, which is 32. You can multiply by 32, which would give you the mass of oxygen. Should be 0.00915 or 9.15 times 10 to the negative third grams, or 9.15 milligrams, however you want to write it. Okay, great job. So if you have any questions, feel free to comment and like the video, subscribe to the channel, but most importantly, I hope this helped you guys. Happy studying and good luck.